So welcome all. Today we are going to learn something about multi-protocol level switching as well as generalized multi-protocol level switching. So this story starts with hierarchical routing actually, where you can understand this router have routing tables, right? So definitely we will have certain ways to keep the routing table shorter, but still we may use different techniques like aggregation or different kind of things we have seen. So but still this, as the number of networks for which its information it has to keep, this routing table may get larger, right? So if this routing table will become larger, in that case searching for a particular path of network, you will have to go through the routing table that for this particular network which paths we should take, and it will take more time, right? So passing through router by router, if it takes more time, then it will delay the packet, right? So this is hierarchical routing. What we are saying is we will have routers at in a hierarchy. Okay, so when these routers will be in hierarchy, what will happen? You will have regional ISP, local ISP, and maybe leaf level ISPs and so on. So in this way, they will be responsible for a small number of network, and thus they will be able to handle these routing tables much fastly. This is what you have to see in hierarchical routing. But still there is something that we have to learn here today, is forwarding of those packets not based on just IP address kind of those routing information. We will see something about flow levels, right? You have seen IP version 6 in which we have flow levels, right? So when we want to transfer something, you will see in multimedia also that we want to transfer a flow of packet, right? In that case, these packets will have same characteristic, same properties, same fields, same values, and same path they will try to follow, right? So here we are going for forwarding of the packet based on label, right? So in this coming figure, we are going to see something about a simple example where we are going to see based on longest match algorithm, where we will send this thing, our packet, based on the longest match in the table, right? Doesn't matter, we have efficient algorithms as well, but the main thing is they all match and find out the best option, right? So it also needs to apply mask. So there is a mask column as well. So it then needs to check the network address in the table until it finds the match. The router then extracts the next hop address and the interface number to be delivered. This is something here. So here this is the packet which is to be transferred. So in routing table it will go through this thing, the best match, it will find the mask, okay, and then get the next hop address, and then it will transfer to the next hop, no problem, right? So this is a simple example of searching in a routing table. right? It is not based on flow level till now. You will see in next figure about the flow levels. This is just forwarding based on destination address. You have destination address. So you search in the routing table using a longest match algorithm, and then when the forwarding algorithm gets the destination address in the packet of the packet, then it sees the mask column, and then it also checks the network address, and it checks the network address until it finds the match, right, and then corresponding hop address is transferred. So that is how this routing table based on destination address would work. Now we are going to see what is MPLS, multi-protocol level switching. So for that we have to understand this thing, which is this switching table based on flow levels, right, based on labels, I should say. Okay, so forwarding based on label. So in this figure you have to see that you are using an index table. Here all these address, I should say the index is the label, and in this packet, in place of having whatever mask or network address, you are having label. So if a router maintains this information about labels, for this label this is the entry, maybe certain labels, certain indexes would be empty, but this will help you in direct access. Okay, if this label is already present in packet, just you will check the label and find the entry. Okay, this is the next label, you will keep the next label and send it to the next router. Okay, you will not need to go through, apply any algorithm and go through checking and finding the best option, finding your option or whatever, right. So using this label will improve the efficiency of your transmission. Okay, so this is what you have to understand. So okay, wait. So now, okay, so here what you understand in MPLS, that suppose you don't have MPLS routers right now, if means in certain network. In that case, what you can do is you will replace these your conventional routers with MPLS routers that could support these behavior. The MPLS routers will behave as routers as well as switch also. Okay. So when behaving like a router, MPLS can forward the packet based on destination address using that particular routing table, and when behaving as switch, it will use this switching table and forward the packet based on label. That is, we have to understand. Now, although in version 6, IP version 6 packet format you have seen, we have field, it was flow level. So there is information about flow level, but now here we don't have, in IP version 4 it was not present any flow level. So if at all we have a network where we are using IP version 4, in that case what we can do is we can keep this IP datagram along with header and payload and encapsulate it within another packet with MPLS header, and then we can transmit it. So that is what we have to understand here. Here in MPLS header you will have something like label, experimental field and time to live. Let me show you. So you will have the label. This is label means it will be 20 bit field. This will define that the particular index in the table, and then this is 4 bit reserved for experimental purpose only, 3 bits actually. 24th bit is S. This is actually a stack field. It defines the situation of I should say the subheader in the stack, right. So, if this bit is 1, in that case it means that the header is the last one in the stack. Okay. This is time to live. You understand it was same time to live field as it was in IP datagram. So, now these are something information about MPLS. Now, if we talk about generalized MPLS, in that case you can understand the thing is you are going through this MPLS, you will have this flow label and then you will see those other tables, right. Is there any other way to make it more fast? So, generalized MPLS says that okay, let us consider these switches as labeled switched path and label switched router are there, it will have the label switch path, right. So, in this router what you can do is now in place of going into table, you can use some of another schemes to decide where to send the packet, what will be the next hop, right. So, this can be mostly you can see here 3 schemes are there using the time slot to identify the label switched path on a time division multiplexed link. If at all the link is wavelength division multiplexed, in that case you can use the wavelength, particular wavelength to identify the particular label switch path. You can also have this thing if at all it is fiber optics, or you can also use the particular port that the signal is coming through this port only, then you can identify that what can be the label switch path for this thing. So, in this way you will not need to see the table, you can understand that label switch paths are therefore implicitly labeled in the generalized MPLS. So, on certain network when you want to establish a circuit switching kind of thing, that logical path has to be set. In that case, whether it is time division multiplexed or wavelength division multiplexed or anything, you can use such options for generalized MPLS. So, other than this, the forwarding operation of the router as well as the GMPLS network is similar to MPLS and so on. So, this is what we have learned today in this video, MPLS and generalized MPLS. That is all. Thank you.